Okay, so we're going to do a phasor problem in chapter 10. And so I've already got it on the board for you. So we are given this circuit here. And this is shown in the time domain because we're given the voltage source as a function of time. It's a sinusoidal voltage source. And so we've got, a capacitor, we've got a couple of inductors. Actually, this is a fourth order circuit. So the beauty about AC circuits, okay, this is an AC circuit because it's got a sinusoidal forcing function. If we do not care about the transient response, which a lot of times we don't, really we only care about the force response because the transient response dies out like in a couple of milliseconds usually or less. So if we only care about the forced part of the solution of a circuit which is sinusoidally driven, an AC circuit, then we can use phasors. That's the whole idea of phasors, is that we transform everything into what we call the frequency domain. And we do that by transforming all the voltages and currents into a phasor and transforming all of the elements, that is a capacitor, an inductor, or a resistor, into impedances. And then we get a picture of this circuit. This is in the time domain. We can redraw it in the frequency domain. And so what we're doing is we transform, well, in this case we've only got one voltage source, but we transform the voltage into its equivalent phasor. And there it is. A phasor, you basically take the sinusoidal function, and it's got to be in the cosine form. And so you might have a phase angle. In this case, let me show it explicitly, the phase angle is 0. So you show your sinusoid, you got to make sure it's a cosine. If it's a sine, then you got to change it to cosine, and you can do that with a, forget if you add 90 or subtract 90, but there's a formula. So you take the magnitude and the phase angle, and that's all you need to do to show it as a phasor. So what's a phasor? A phasor is a voltage or a current in a sinusoidally driven circuit where we're only interested in the forced response. So the phasor is just the magnitude and the phase angle of that voltage or current. In this case, it's a voltage, as you can see. Then, and actually, here's a current source. So right now it's a current-controlled current source. The current that controls it is this current here through this branch with the 5 ohm resistor. Okay, so to transform that into a phasor, I'm just going, instead of showing it as a small I sub 1, which, by the way, remember the small letters usually indicate that they are functions of time. And it will be a function of time because it's a sinusoidally driven circuit. But I'm going to show this current as a phasor. So I'm going to give it a capital I1. I don't know the value of this phasor, but it's going to be some magnitude times cosine with a phase angle. So really the only unknowns are the magnitude and the phase angle. And the reason that we only care about the magnitude and phase angle and we don't care about the frequency is because the frequency is going to be the same for all currents and voltages in the circuit. So you might want to just note that frequency, like maybe as a note by the picture. So the frequency is 2. Okay, so this is the angular frequency as opposed to the regular frequency anyway. But usually it's just fine just to show the angular frequency. So this is called the frequency domain. So you transform all your voltages and currents into phasors and any element into its equivalent impedance. All right, so for a capacitor, you have to know that the impedance for the capacitor is Oh my God, what's the formula?
1 by G, 1 by
What is 1 over
omega C.
omega C like that times
Yes,
J,
J
like
by
that?
J.
Or is J in the denominator?
Yes.
Yeah, okay, thank you. So the impedance for a capacitor is 1 over omega Cj. The impedance for inductor is just omega Lj.
Yes.
And then the impedance for a resistor is just the resistance. Okay, so using these formulas, that's how I got the impedances for each of these elements. Notice the impedance for the resistor is just the same as the resistance, so it's 5. The impedance for this inductor, omega Lj, so that's how I got the 2J, because L is 1, omega is 2. Okay, so that's how I got all of the values in these boxes. And by the way, the boxes represent impedances. So you take each element. Okay, so once you decide that you're going to solve your problem using phasors, and you decide that by just noting that you've got a sinusoidally driven circuit and you're only interested in the forced response. Once you realize that, you go ahead and you transform it from the time domain into the frequency domain. Once you're in the frequency domain, the problem is just like a resistive circuit. You solve it using node voltage analysis or mesh current analysis. The impedances are just resistances. You treat them like resistances. Now, of course, they're complex numbers. So you're going to, it's the math is going to be harder because you're going to get all these equations with complex numbers. And so if you don't know how to deal with complex numbers, then you're going to have a problem. But I want you to understand that in the big picture, once you go from the time domain to the frequency domain, you've reduced your problem to a simpler problem of just a resistive circuit. But instead of resistances having real values, you've got imaginary numbers. So let's go ahead and solve that. So I'm going to erase this. Okay, we don't need the time domain anymore. I'm looking for the current I1 in the time domain, but once I find it in the frequency domain, I can easily transfer it back to the time domain. We are given some values for V2 and V1 in the time domain. So looking at this, V2 in the frequency domain, where's V2? There it is. It's that node up there. It's in that node in the middle. We were given this. So the phasor V2 is really, it's just this magnitude times the phase angle. And then V3 is this magnitude. And then its phase angle is minus 69.8. Okay, so here's the phasor representation of that same voltage. Here's that voltage in the time domain. Okay, it's very easy to go back and forth because all you need to do is look at the magnitude and the phase angle. And that's all you need for this complex number here. And this is, what is this? This is the complex number in polar form. If you don't know what I mean by that, go review your complex numbers. Okay, I need this space. All right, so let's see. So we're asked for I1. So I'm going to do Kirchhoff's current law right there, because I can see that I'll get I1 in terms of I2 and I3, and I can easily figure out I2 in terms of V2 and V3, which are given. Oh yeah, I'm there already. I see. I've got this baby nailed. Okay, so Kirchhoff's current law at node, what do I call that node? Node 3. So we have the phasor current I1 coming into the node. Okay, I always take those as negative. Plus I2, because that's leaving the node. Plus I3 is equal to 0. So, okay, I've got I1 is equal to I2 plus I3. I2, just by inspection, looking at I2, we know it's V3 minus V2 over that impedance. Because this, this is just like, pretend that that's a resistance, but it's a resistance with a complex number. So I2 is equal to V3 minus V2 over J10. I3, similarly, is V3 minus 0, because that's the reference node on the other side. So it's just V3 over minus J2. So I'm just going to, okay, V3 is given, we have it here, 0.6064 minus 69.8, all, oops, minus V2. Okay, so we've got some kind of ugly complex algebra. That's okay, all over J10. Okay, so this is V3 minus V2, and then V3 here is 0.6064, angle minus 69.8, all over minus J2. All right, so you have to know how to add and subtract using complex numbers. Here we have this complex number subtracting this complex number. The problem is, it's really hard, well, you have to convert the polar form of the complex number to the rectangular form. So you got to convert this to the rectangular form, this to the rectangular form, then you can carry out the subtraction, then you convert it back to polar form, and then you can do the division. Okay, cut.